sort of values here. These values, if you come to the exam and you tell me, and I ask what the pi is, and you say 3.14, then you fail, right? Okay? So you should know that this is not a number, but it stands for a coefficient that is a measure for how strong the piezo-resistive effect is in silicon. This is dependent on the doping, and it's also depending on the orientation, because it's a crystal, so it's direction dependent. And we went through a whole argumentation that if you orientate this now along a certain direction, the 110 direction, then you get numbers for the transversal and longitudinal, so L and T here. Sometimes parallel and perpendicular sign is being used, yeah. Then you get numbers here of plus 72 and minus 66. These numbers are not exactly the same, but they are rather comparable. And then we went through a whole argumentation of if you have a square membrane, but you can also extend this to a round membrane. Where to place them? If you place them like that, you get an increase in resistance. If you do it like that, you get a decrease in resistance. And yeah, this is basically how far we got. I think the last slide I showed you was that one. So this is now a conceptual drawing of a pressure sensor, how you would make this. Yeah? So you have a membrane here, square-shaped membrane. You place two piezoresistors parallel on the edge, so the other one is not shown. It's in the cutaway, in the cutaway section, and the other two you place perpendicular along the 110 direction, and then you have two resistors where the resistance increases and two where the resistance decreases due to the mechanical stress that you generate if this membrane here is being deflected up and down. So that's the general argumentation. Now, of course, there's much more detail to the actual design of such a sensor. Some of the things I'm going to mention now in the following, but only the most important one. One of the first questions is how big do you make these things here actually? So, in comparison to the membrane, and here's a measured graph where they relate the mechanical stress to some sort of maximum, so it's normalized to 1, whatever this maximum is. Could be the maximum stress generated by a pressure that you want to measure with your device as a maximum pressure. And you relate this now to A, which is the side length of the membrane, and then you get a graph that looks something like this here. So it's this ratio here determines the sensitivity. And if you make the device here smaller, then you get a sort of a non-linear effect. So here you have a large linear portion, but here you have an effect that if you make it too small, then the sensitivity, which is the slope, effectively is getting less. So that's one of the things you need to consider when you, in fact, design this. And there are papers on this, and many research theses have gone into devising procedures on how to optimize the actual size. But the message here is, all I want to say here is the smaller you make it, if you make it too small, your sensitivity is going to suffer. Okay, so let's go back to the previous conceptual arrangement. So here you have your 4 resistors. And of course this begs to be arranged in a Wheatstone bridge, which we had talked about last time. One of the big advantages of the Wheatstone bridge here is that, this membrane here is maybe a millimeter or a few hundred micrometers, and you can make to a reasonably good assumption, to a reasonably good approximation, the assumption that the temperature these 4 resistors see here is about the same. So if you have a temperature increase of your pressure sensor, let's say it sits in the engine of a car, you start it cold, engine heats up, this is a common mode signal, and by measuring then, which is not shown here, the voltage from here to there, across there, then you have in this voltage measurement, due to this Wheatstone bridge configuration, your temperature dependency becomes a common mode signal. So the first approximation, it cancels out. Okay. Now this is really up to only first approximation. If you have a real pressure sensor for whatever application, automotive, medical applications, and so on, the temperature sensitivity, despite having this Wheatstone bridge configuration with this first order cancellation, despite that, this temperature sensitivity is a big problem. One of the biggest problems actually there is in making real product, high precision, long lasting, not drifting away pressure sensors. And I talked about the medical applications, implants in the eye and so on. I talked about last time. You can say in your body, we are mammals, so our body temperature is always the same. But even this tenth of a degree difference of having, while doing sport, for example, or just lazing about on the sofa, can have an influence on the body temperature in such a way that the pressure sensor and the signal you're getting is affected by that. So these temperature sensitivities are a big problem in many applications for pressure sensors. Okay, now the slide I began with the lecture today, plus 72 minus 66 pi L versus pi T. These numbers are not exactly equal, and what you can do is you can play around with tricks like that. So making them by the size or doubling the numbers at certain places, you can by design make this really, well, not exactly the same, but an approximation, so that these two numbers, this 66 and 72, become more equal, closer to in order of magnitude to each other. So people have played around with this also. So you can play around with the design here, the numbers, the lengths, where exactly you put them and so on. No? So again, many different approaches and design work and research has gone into that. Yeah, if you do this, you get also, well, you have a sensitivity. The sensitivity at the output is per pressure, so per Pascal or per bar or per torr. Doesn't matter really what unit you use. But what also influences is here the V, and the V here is basically what kind of voltage you feed into your Wheatstone bridge. So that's another parameter that influences your sensitivity. So and this is why you look at a data sheet, it's quoted as millivolt per volt per Pascal. So this volt here, this is effectively the voltage you apply to the Wheatstone bridge. Okay, so you can play around with this. There's of course a trade-off. The higher the voltage, the more the current flows through. So you burn more power. Maybe you have some self-heating of the resistors because it's a resistor, so it always has a dissipating effect as well. So it gets warm and so on. So these things you have to also take into consideration. Now, what I haven't said really about is how to make these piezo resistors very much from the fabrication point of view, because we've kind of finished with the fabrication chapter. Again, fabrication chapter brushed over many things and did not go into depth. So you can make, of course, these. You have your silicon wafer here, and you want to make, let's say, you mask a part of it, and you want to make a piezo resistor here. Yeah, there are several ways of doing this. Yeah? So what's mentioned here is diffusion. So you have some sort of gas here that contains a dopant that penetrates into your silicon wafer here, and you heat this up, of course. Diffusion only takes place at high temperatures of, well, let's say around 1,000 degrees. And of course, how long and how hot and the concentration of the gas and so on will have an effect on how your profile of your piezo resistor looks like. And what's mentioned here is shallow diffusion and deep diffusion. So some sort of measure of how deep the, in this case would be boron, yeah. If this is an N-type silicon here, the P dope part would be the piezo resistor. Boron doping, yeah, how deep the boron goes into, and the longer you wait, and the hotter you make it, and the higher the concentration, and so on and so on. Many parameters. The deeper will be the diffusion. So there's another parameter you can play around with, and the kind of main effect is summarized in these two bullet points here. If you do a shallow diffusion, so this is the first case here, then you have the problem that you have a nice sensitivity really to the surface stress here, and that's what you really want to measure when your membrane is deflecting. But you buy this higher sensitivity with the unwanted effect that you get a less stable signal. So this shallow diffusion piezo resistors, they are prone to long-term drift effects, due to surface charge effect. So here you have some surface charges that are accumulating there, and so on and so on. let's not go into the physics, yeah. But the shallower you are with your boron diffusion here, the higher the sensitivity will be, but the less stable it will be. Yeah? So it's always like that, it's no free lunch. Yeah? So for example, if you want to make a medical implant, it's maybe something you want to avoid, yeah? Because this drift and stability over time is a major issue. Then you can say, okay, well, I go deeper. So all the dotted lines here, that's fine, but because you're deeper, you don't measure the surface stress anymore. This is not to scale, of course. This line will be somewhere down here. Maybe if it's to scale, diffusion here is only a few micrometers of the entire wafer thickness. So if I go a bit deeper, then the sensitivity tends to degrade because I kind of average over a strain, or stress I should say, over a strain gradient into the bulk of the material. Okay. So, and of course you can have a trade-off now there, you can find for your application what is the best. So here's a picture of a real thing here. The actual chip sits there. And then of course you have to package this somehow. Huh? With this packaging, I'll come back to this a bit later, you also introduce a bag of problems. A real can of worms is actually the packaging. It's actually, too often, to a large extent, it's the most challenging part, especially for pressure sensors, but also for other sensors where long-term drift effects, accelerometers, gyroscopes are important. The packaging is actually the most difficult part, but nobody likes working on this because it's not a sexy topic and so on. I said this already. Packaging is boring, so people want to really, I want to make a new chip, a new design of my little silicon chip, and then they put it into a package and then it does completely other things than what you expect. So I'll come back to that a bit later today. In the meantime, I just want to show you some examples. So this one was one of the first commercial successful MEMS pressure sensor by Nova Sensors in the US. So what they have is a Pyrex or glass wafer or substrate which is bonded to this bulk micromachined KOH etched typical slanted or sloped sidewalls here. Yeah. The P-type substrate, and here we have an N-type epitaxially grown layer. Any idea why they use this N-type epitaxial layer? Mechanically, it doesn't make much difference. A bit maybe, but not very much. Why would they have this here on top of your nice single crystal P-type?
So to stop the KOH process.
Yeah, good. Yeah. So it's a KOH etch stop. It's an electrochemical etch stop they use, which I briefly explained in a few weeks ago. Yeah. So this allows them to really create here a fairly process-independent, uniform membrane thickness that is really stable over from one process batch to the next one. And otherwise, if you don't do that, each of your pressure sensor batches, wafers or so, will have completely different mechanical sensitivities. Somehow this spring constant, the trampoline, so to say, is goes with the power to the 3 of the thickness here. If you look at this up in a mechanical textbook, then you find there's a very strong dependency on the thickness. Okay, and what you also see here now are the piezoresistors. So P-type diffused piezoresistors. So this here effectively in the N-type epitaxial layer on the edges of the membrane. This parallel and these ones here perpendicular. And the entire thing is bonded. And now to the Pyrex wafer, and the Pyrex wafer has a hole here. Now of course you need to have a hole there because you need to have the pressure you want to measure, have an access to your membrane that is going to deflect. Otherwise you can't measure the whatever pressure you would like to. Now this is fine to some extent in air, but if you are now in a, let's say, environment like in a, let's say, have a hydraulic system where you want to measure the pressure of the incompressible fluid, oil, most of the time. The oil is dirty, it's hot, it's corrosive, and similar arguments you can make with blood, if you want to implant this. So having the blood or the oil directly pushing here on the silica membrane, that's not going to work for a very long time. So that leads to this packaging problem. Right? And again, I'll come back to this in a moment. So here's Wheatstone bridge. That's the same thing as before. This equation I've shown you as well. The pressure here. Yeah. So here you see the bond wires as well. Right? This is a different design now. This is a design that comes actually from us here in Leuven. It was before my time, so this goes back to maybe 10-15 years or so. It's the same approach. It's if you compare this to the other designs I've shown you, you see this elongated shape here. So not a square, but the membrane is square, but the contact and so on is elongated. Any idea why? Do you want to make this like that? This form factor here? No? Why is, yeah, please, yeah.
Prevent the lens from affecting the vision.
Preventing what?
The lens of the conducting cable.
Yeah, but I could shorten those. If I make all the contacts on the side and I have a square,
Then they would be unequal.
they would like that, they are unequal. If you look at this line here, this is longer than that line. If I make a square one, I could make all lines the same. Right? So actually, in terms of the line width of the metal line tracks here, this is probably not such a good idea here. So think of what determines here the form factor is actually the end application. So this was intended to go into an endoscope. So a medical tube that they stick into your body somewhere through all sorts of holes, artificial or natural, and this was the idea to integrate here a pressure sensor that gives you an indication of the pressure inside some of the body cavities that you can access with a knee hole surgery or gastritic investigations and so on. So here's the fabrication process. So we have here a double-sided process. So we have to do some processing at the front. Here the boron implantation. Yeah. And at some point we have to make here the KOH etching to form to form the membrane. And if you now have the membrane, or this KOH edge cavity, a little bit misaligned, left-right, then your piezo resistors will not measure the same thing anymore. So they don't sit on the or at the right locations as in my drawings before on the slides, where they always sit at the same distance left and right from the edge of the membrane. So I have to somehow align this here with my cavity etching here. So here, same as we discussed already, electrochemical etch stock. This is the epitaxial. In this case, it's an N-type layer and a P-type single crystal silicon. So it's just the other way around. That works as well. It has been done as well. So I come back to that alignment problem here, front to back side. So you use here alignment masks or marks. Okay. So what else? We have a nitride mask. Where is it? Here. This is a nitride, silicon nitride etch mask, which is opened, and you put some aluminum contacts here. So these are the metal tracks. You make the electrical contacts here. Making electrical contacts from metal to silicon is also an art by itself. So people who followed the technology course, technology course last year, they know that. All sorts of spiking and pitting and all sorts of stuff can happen there. Yeah? So we brush all this under the table. So we have an oxide and a nitride layer here, these two insulation layers. And then the last step is this electrochemical etch stop. So apart from the problem with the alignment, that's I'll get back to that in a moment, as I said. If I want to make money with this, then I want to have as many chips on a wafer as possible. And this KOH etching requires space because it always gives you this sloped 1-1-1 sidewalls. So from a commercial point of view, if you could make this like that, vertical, the etched side wall, then I can save space on the wafer. So modern pressure sensor fabrication flows, they would replace this here with a deep reactive ion etching, what we talked about before. Now there's the whole commercial aspect to this. Of course, to make this, to etch this in a KOH, it requires, at the end of the day, a few beakers and a fume hood, so not so much equipment. So in that sense, it's cheap. Deep reactive ion etching.